So differentiating exponential and logarithmic functions. Okay, that's what we're doing today. So let's do first a review. So first, a review of exponents. Okay, so I'm sure you're very good at this, but it's always good to review. Okay, so let's go to the first thing, definition of exponents. A power m is equal to a times a times a times a. How many times? It's a times itself, of course, m times. Okay, so this, I'm sure you've been learning this since elementary. Then let's write down all the properties of exponents. So first, a power m times a power n equals what? What is it?
A power m plus n.
So a power m plus n, so everybody knows this. A power m divided by a power n is, of course, a power m minus n. Then a power m to the power of n is what? What's this one?
A power m multiplied by n.
So a power m times n, good. Then a power 0, what is that?
1.
What's a power 0?
1.
1, okay, of course, only if a is not 0, right? If a is 0, then we have 0 power 0, and that's a bit complicated. Okay, we'll do that soon. Another case, another situation, a power negative n, what is that?
1 over a.
1 over a? Just 1 over a?
N.
Or n over a, sorry.
Sorry? 1 over what? I didn't hear, I'm sorry.
1 over a power n.
Good. 1 over a power n. Again, with a is not 0. If a is 0, then we have 1 over 0, and that's, you have to do a limit for that. And the last one, a to the power of 1 over n. What is that?
A root n.
The nth root, very good, nth root of a. Okay, so these are my 6 rules, 6 basic rules for exponents.
Sorry. One of the girls just texted and said that they're in the waiting room, but she wasn't letting because she thought the class started at 2:30.
Okay, she did not. Thank you.
No problem.
Okay, so this is for exponents. Okay, so do you need examples for this or you're fine? I think you're fine with this, no?
Yeah.
Okay, anyways, if you need practice, you could go always on the pre-calculus worksheets and you're going to find exponents and logarithms there. Okay, so now let's go to logarithms. Okay, so let's first write down the definition, just like I did here. So the log in base b of x equals y. What does this mean? This is equivalent to saying what? That b power y equals x. Okay, so this deserves an example because this is a bit twisted. For example, log in base 2 of 16 equals to what? What's 2 to the log in base 2 of 16 is what? So
4.
you ask, what is it?
4.
4. Perfect. Okay, so this is 4. Why? Because 2 power what gives me 16? Well, 2 power 4. Okay, so since 2 to the power of 4 equals 16. So when I'm asking you to evaluate the log, what you're actually finding is the exponent. You're finding what should I put the base to the power of what should I put the base to get 16. Okay, my base here is 2, so you put it to the power of 4. Okay, and of course, when you were in high school, you probably did a lot of examples like this. I'm going to spare you for now, but I am going to write down the 4 important rules of logs here. Okay, so the first one is that the log in base b of x plus the log in base b of y equals what? What is that equal to when you add 2 logs of the same base?
X plus y.
No, it's log in base b of x times y. Okay, and when we minus log in base b of x minus log in base b of y, what do we get? Log in base b of
X divided by y.
x over y. Good. Then the log in base b of x to the power of a certain number a. What can I do with the power a?
Put it in front of the log.
Put it in front. So it's a times log in base b of x. And the last one, log in base b of x divided by log in base b of y is equal to what? Anybody remember this one? Okay, so the y becomes the base. So log in base y of x. Okay, so these are my 4 main properties of the log. Of course, we should prove them. You probably, hopefully, have proven them in high school. If we have time, we'll prove it. It's not that difficult, but since we're already into derivatives, well deep into derivatives, might as well just go to the derivatives and just know these rules because you're going to have to use them. Okay, and if we have time, we'll prove them. Okay, so what I'm going to do is maybe give you one example of each of how this works. Okay. So example, let's say log in base 6 of 4 plus log in base 6 of 9 equals what? Okay, so according to my rule, you put the base log in base 6 and you multiply the 4 and the 9. So you multiply 4 times 9 is 36. And log in base 6 of 36 is what?
2.
6, right? Good?
Isn't it 2?
Yeah, it's 2, okay? Just want to make sure you're awake, okay? So it's not 6, okay? It's 2, okay? Because 6 power 2 is 36 and not 6 times 2 is 36, okay? It's power here. This operation from here to here is power, not times. Here, log log in base 2 of 40 minus log in base 2 of 5 is what? So according to my rule, I'm going to minus, so I divide the inside. So it's log in base 2 of 40 over 5 is 8. Okay, and what's it going to be here? Log in base 2 of 8. What is it?
3.
3. Okay, not 4, 3. 2 power 3 is it? Log in base 3 of 27 to the power of 12, let's say. So I'm going to put the 12 in front. 12 times log in base 3 of 27. And log in base 3 of 27 is what?
3.
3. So 12 times 3 is 36. Perfect. And last one here. Log in base 15 of 32 divided by log in base 15 of 32. Sorry. Oh, yeah, the answer of 32. No, not of 32. Let's say of 2. What is that? Well, my rule tells me that it's log in base 2 of 32. And that's equal to what?
Five.
Perfect. 5, because 2 power 5 is equal to 32. Any questions? Okay, let's continue. So a few definitions. Okay, first thing is what we call Euler's constant. Okay, and that's E, which is 2.718281828, and it keeps going. Okay. And how do you evaluate this limit? I'm sorry, this value. Okay, so E is equal, so here's a definition of one of the definitions, is when x approaches to infinity of 1 plus 1 over x to the power of x. Okay, so notice that if I plug in infinity here, what do I get? 1 plus 1 over infinity is 0. So 1 to the power of infinity. Okay, so this is also an undetermined form. Okay, so even though 1 power anything is 1, but 1 power infinity, it's not 1 anymore necessarily. Okay, it's an undetermined form. Same as 0 power infinity, things like this. Okay, so we're gonna deal with these later in the course. Okay, but for now, know that 1 power infinity is an undetermined form, and you could check. Let's check. Let's plug in this in this expression, let's plug in a very, very big value of x and see what we get. So I'm going to plug in, let's say, 1 billion. So 9 zeros, 2, 3, 1, 2, 3. Okay, so 1 billion, so 1 over this, plus 1. Okay, so what inside the bracket, I have 1.000001, and I'm going to put it to the power of x, which was 1 billion. Okay, I get, there you go, 2.718281827. Okay, and well, the real is it's an 8 here, and of course it keeps going forever. It's an irrational number, just like pi and the square root of 2. This is a irrational number. Okay, any questions so far? Okay, another thing, ln of x. You know what ln of x is?
Log base 10.
Nope. Log in base, it's log in base something, but not 10.
Log base e.
Yeah, it's log, and the base is this number, this weird number here. Log in base e of x. Okay, and then log of x. So log without anything on the bottom. What is the base? This is the base 10. Okay? Any questions? Okay, if there's no questions, I will continue. Okay, so let's go straight to the derivatives right away. All right, so there's 4 of them I want to talk about. So if f of x is equal to the ln of x, then if f of x is equal to the log in base a of x, then if f of x is e to the power of x, and then if f of x is any number a to the power of x. Okay, so in each of these cases, I want to find the derivative. So f prime of x for each one. Okay, so the derivative of ln x is what? Anybody knows it?
1 over x.
Good. It's 1 over x. The derivative of log in base a of x. Let's say the base is not x. It's not e. It's a. Any number. Let's say 2 or 3 or 20. Who cares? How do you find the derivative of that? So it's still 1 over x, but I have to also divide by the ln of that number, the ln of the base. Okay, we're going to prove all this, of course. Okay.
That's what you mean when you say like we have to multiply by the ln of a. Like, will you give examples?
Of course. Of course. Okay, we'll give examples. And e power x, the derivative of e power x is just e power x. It stays itself. Okay, that's what's so crazy about this number. If you do 2 powers 2.718281828 power x and use the derivative, the slope is exactly equal to the value of the function. Okay, we'll talk about that soon. Okay. A power x, the derivative also stays itself. A power x, same thing. So if you have 2 power x, derivative is 2 power x times, you have to do again ln of the base. And these are your derivatives for exponential and logarithmic functions. Are there any questions? Okay, so I'm debating whether to prove or to do examples on applying it first. What do you think you prefer?
Examples.
Example first, so let's do a few examples. Okay, just basic ones. Just easy examples at first, then we'll prove it and then we'll go to the more complicated ones. So find f prime of x. Okay, so first, let's say f of x is equal to x2 times ln of x. Okay, so what's f prime? Of course, we have to do the, which rule?
The product rule.
You have to do the product rule because it's a multiplication. So let's go. Derivative of the first times the second plus the first times the derivative of the second. Okay, and that's equal to 2x, we know. So 2x ln x plus x2 times, and we just said, right? I just stated that ln x, the derivative is 1 over x. And that's my answer. Okay, of course, you could maybe simplify this one. x2 over x is x, pull out an x. So x times 2 ln x plus 1. You could write like this. Okay, I simplified here. We never usually simplify, but this is tempting. Okay, second one. Let's say f of x is 3 to the power of x5. Okay, so f prime of x will be, so try it. Take a few seconds, take a few minutes, try it. I'm going to post maybe another one. Number 3. Okay, not too complicated, just to warm up to it. So the derivative of, so again, the chain rule here, 3 power a function. So 3 power anything, the derivative stays 3 power this. Times whatever the function is, which is, no, it's 3 power that thing, times ln of 3, times the derivative of the exponent. Okay, and that's it. The rest is easy. So 3 power x5 times ln of 3 times 5x4. That's my answer. Okay.
Like ln of 3, we leave it like that, right? That, like we don't say.
Evaluate this?
Yeah.
No, you don't need. I prefer this. I don't want decimals. Okay, now f prime here. So the derivative of log in base 5. So it's 1 over what's inside. So 1 over tangent x2 times ln of 5 times the derivative of the inside. Right, my usual chain rule. Okay, and this we know how to do. We've done this a lot. So it's 1 over tangent x2 times ln 5 times the derivative of tangent is secant squared of x5 times the derivative, of x2 times the derivative of x2. And so 1 over 10x2 ln 5 secant squared x2 times 2x, and that's my answer. Okay, any questions? Okay, we're going to do a lot of these soon, but let me now just prove the differentiation rules here, derivatives of ln, log, and all these. Okay, so I'm going to start with proving ln x, which is definitely the hardest one. Okay, let's go. So proof. Okay, so the proof of that if f of x is ln x, then I want to show that f prime of x is 1 over x. Okay, so let's start. I'm going to use the limit definition of the derivative. Okay, so f of x is equal to ln of x. So f of x plus h is what? What's f of x plus h?
Ln of x.
Ln of x plus h.
Ln of x plus h. Good. And so f prime of x will be the limit as h approaches 0 of f of x plus h, so ln of x plus h minus f of x, which is ln of x, and all this over h. Okay, let's just simplify this a bit using the properties of logs. So limit h approaches 0 over h. And I know now, we know that if you subtract two logs that have the same base, like we do here, they both have base e, you could write them in one log and this divided by that. So x plus h divided by x. Is this okay with you guys? Okay, so I didn't do anything crazy. I just combined them using the properties. Then I'm just going to fix it a bit. I'm going to put, instead of dividing by h, I will multiply by 1 over h. So limit h approaches 0. So instead of over h, I'm going to write 1 over h times the 1. Okay, same thing. This and this is the same. And the inside, I'm going to fix it a bit. So x over x is 1 plus h over x. So the same thing. Yeah, I just separated the fraction into two. X over x plus h over x, here they are. Questions? Okay, let's continue. And the last transformation, algebraic transformation here I'm going to do is I'm going to bring the exponent here on top here. I'm allowed, right? The exponent could move freely from here down in front of the ln. So I'm going to re-put it back on. So ln 1 plus h over x to the power of, and this is 1 over h. Okay, so basically all these steps, they all mean the same thing. Okay, so definition of the derivative with some algebra, I wrote it this way. Any questions? Okay. So now comes the tricky part. Okay, so I'm going to do a substitution here. So h over x, or x over h. Okay, x over h, I'm going to call it n. I'm going to call this n. Okay, I decide. Every time I see an x over h, I'm going to call it n. Okay, then if I send the x on the bottom here, I will have one. If I divide both sides by x, I will get 1 over h equals to n over x. Okay, so that's the tricky part. Okay, so again, I'm doing a sort of a change of variables. Every time I see x over h, I call it n. Okay, so if I isolate to 1 over h, I'm going to need 1 over h because I have 1 over h here. Okay, so 1 over h is equal to n over x, right? You send the x on the bottom. Okay, if you do cross multiply, okay, so you send the x down here, becomes n over x equals 1 over h. And what can I notice here is that as h approaches 0 plus, okay, well, n approaches what? Okay, so if I divide a number x by 0, right, we know that we're going to get plus infinity or minus infinity, or doesn't exist. Okay, but since we're dividing by a positive, so it's a number over 0 plus, so n will be plus infinity. Is this okay? You don't have any questions, and this is not easy. So either you're completely lost or you're geniuses.
Sir, I don't really understand the last part where you said n approaches positive infinity.
Okay, is this okay, this step? Everybody's okay with this?
Yeah.
Okay, now this one here, okay, so if h is approaching zero, then what's going to happen here? I'm going to have x, a number, divided by 0. And we know that if we divide a number by something very, very, very small, I'm going to get something very, very big. So the closer h is to 0, the closer n is to infinity. Does this make sense?
Yeah, thank you.
Okay.
Can you explain again?
Sorry?
Can you explain again how did you get 1 over h equals to n over x?
Sure. Okay, so this is my substitution. This is what the transformation I'm doing. The only thing I did here is I divided by x here, and I divide by x here. And this will cross out. You'll have 1 over h, and here you'll have n over x. You get it?
Yeah, okay.
I divided both sides by x.
Okay.
Okay. Now I'm expecting a question which I'm not getting. That's why I'm stalling a bit, because I'm waiting for you guys to ask me a question.
But from where did you get like x over h equal n? Like, did you just like guess?
Oh
it?
yeah, I came up with this. Okay, don't worry too much about this. Okay, if you do enough math, you're gonna get you're going to get used to these kinds of substitutions. Okay, but I don't think, I think you could handle all of CJAT probably without having to know these things. Okay, I just have to show it to you because I'm showing you the proof. Okay, so my question is, okay, so I told you as h approaches 0, n is approaches plus infinity. Everybody was convinced with this because if I divide x by a 0 positive, I'm going to get plus infinity. But what if the x is negative? Nobody asked me this. Right? If x is negative, then I'm going to have negative over positive. I'm going to have minus infinity. Do you understand my question?
Can you repeat it?
Yeah. I'm questioning why is this plus infinity? That's what I'm questioning. Okay? You definitely can't accept everything I tell you. Okay? So I'm telling you that when h is approaches 0 plus, well, n is approaches infinity. Why? Why? Because if I have here x divided by 0 plus, well, we said you're dividing by 0 plus, you're getting plus infinity. Yeah, but that works if this is positive. If this is negative, then I'm going to have negative or positive, I'm going to have minus infinity. That's my question. Okay? So how do we solve this problem? So I wrote plus infinity here. So that means that I'm pretty convinced that my x is positive. Okay, so why is my x positive? Well, let's go back to my function. My function is ln of x. And ln of x is only defined for x positive. Okay, this guarantees that x is positive. Because ln of a negative doesn't exist. It's just like the square root of a negative doesn't exist. Okay, same thing, log of -1 doesn't exist. Okay, well, it exists in the complex numbers, but you're not doing complex numbers. Okay, no imaginary numbers here. Okay, so we're just dealing with real numbers, and if x is negative, then ln x is not a real number. Okay, just a reminder of the log function. Okay, maybe you haven't seen this in high school, so it might be wise for me to show you what it looks like. Okay, so it looks something like this. This is ln x. F of x equals to ln x. So you see that x is definitely positive. There's no, the domain of f, if you want, domain of f is from 0 to positive infinity, not including 0. Okay? So that's why x is positive. And that's why this is approaching plus infinity. Is that okay? Okay. If you understand this, the rest is going to be much easier. Okay, this what I boxed here is by far the hardest part of the proof. Okay, this was just algebra. Now that we did the substitution, now the idea will just be to express everything here in terms of this substitution. Let's see what we get.
I have a question.
Yeah, sure.
How do you know h is approaches to the 0 plus?
Oh, here?
No, I mean as h approaches 0 plus.
As h approaches 0 plus.
Oh,
why did I put a plus here, you mean?
Yeah.
Let's go back here. Okay, let's go back here. If h is approaching 0 from the minus, so again, for the same reason, I don't want to even get close to a negative value inside here. Okay, everything is happening on the right side of the x-axis, on the positive side of the x-axis. So everything is positive. everything is approaching from this side. Do you understand?
So every time is h is approaches 0 plus, not 0 minus?
No. Only in functions like this or square root of x plus h, you're not going to approach it from the left because the square root function also starts at 0. You understand? Okay. So let's complete the proof, and we're going to stop at that here after that. Okay. So let's go back here now. So we were at this point. Okay. So let me now continue here. So limit of ln of, so 1 plus. So now I have h over x. So what's h over x? So x over h is n, right? X over h is n. H over x is what?
1 over n.
Very good. 1 over n, good. And to the power of 1 over h, and 1 over h we said was n over x. Is this okay? Okay, so limit ln 1 plus 1 over n, n over x, and look, I don't have any h's anymore. Now I managed to get rid of the h's, and now it's not h that's in effect now, it's n. So I know that n approaches infinity. So n is approaching positive infinity. So this is my limit. This limit is exactly the same as this one. These two limits are the same.
I have a question.
Sure.
Is this substitution part like absolutely necessary, or does it just make things simpler?
What would you suggest?
Oh, I don't really know, but like, is there a way to do it without the?
Maybe, I don't know. This is possible, but I don't see another way. I have to think about it, but I don't know if there's another way. I would never say never, but there might be an original way, but that's the most natural way to do it. Okay. So let me write down now. Equals limit as n approaches infinity, ln of, so 1 plus 1 over n, and I'm going to do here power n and power 1 over x. This and this is the same thing. Because if you multiply the exponents, right, when you have a power n power m, you multiply the exponents. So if I multiply these two exponents, I'll get back to this. Is this okay? Okay. Why did I do this? Because now I could put the exponent in front of the ln. I'm going to put 1 over x in front. So I get limit as n approaches infinity, the x 1 over x comes in front. So 1 over x times ln of 1 plus 1 over n power n. All good? Then 1 over x does not depend on n, so I could pull that out of the limit. So 1 over x times the limit of the ln, which is the same thing as the ln of the limit. So I'm going to do ln of the limit as n approaches infinity of what's inside, 1 plus 1 over n power n. Okay. And I'm just going to remind you something here. 2 seconds. So remember what I wrote here, limit as x approaches infinity of 1 plus 1 over x power x. That's e. And that's exactly what I have here. Ln n approaches infinity of 1 plus 1 over n power n. Well, that's e. This is e. Okay, so I have 1 over x times ln of e. Ln of e is 1. So I have 1 over x times 1. And I just show that it's 1 over x. So just for you to know, ln of e is equal to the log in base e of e, which is, so e power what gives me e? 1. Right?
Yeah.